In this example, we have three charges arranged on the vertices of a right triangle, as shown in the diagram there. And the question is, what's the instantaneous electrostatic force exerted on the 6.0 Coulomb charge? So to figure this out, we're going to have to figure out the forces that are acting on the 6.0 Coulomb charge, and then add them together. Well, let's start with the force that the 4.0 Coulomb charge is exerting on the 6.0 Coulomb charge. We know that the force is given by kq1q2 over r squared. K is 9.0 times 10 to the 9th Newton meter squared per Coulomb squared. The charges are 4.0 coulombs and 6.0 coulombs. The distance between these two charges is 0.34 meters. Meters cancel and coulombs cancel, and we find that the magnitude of the force between these two charges is 1.9 times 10 to the 12 newtons. There's another charge that's exerting a force on the 6.0 Coulomb charge, however. It's the negative 2.0 Coulomb charge. It's exerting a force that once again is given by Coulomb's law. K is 9.0 times 10 to the 9th Newton meter squared per coulombs. The two charges are 2.0 coulombs and 6.0 coulombs. Remember, we ignore the signs in this equation. And the distance between the charges is 0.48 meters. Once again, meters and coulombs both cancel, and we're left with a force of 4.7 times 10 to the 11th newtons. So those are the magnitudes of the forces that act on the 6.0 Coulomb charge. Let's redraw the diagram emphasizing those forces. The 4.0 Coulomb charge is exerting a force of 1.9 times 10 to the 12th newtons, and the negative 2.0 Coulomb charge is exerting a force of 4.7 times 10 to the 11th newtons. Now let's figure out the direction. Look at the 4.0 Coulomb charge. It's a positive charge, so it's going to repel the plus 6.0 Coulomb charge. So that 1.9 times 10 to the 12 newtons will be directed straight up, straight away from the 4.0 Coulomb charge. Since it's pointing straight up, it's going to make an angle of 90 degrees relative to the horizontal. Now what about the other force? The other force is being exerted by the negative 2.0 Coulomb charge. It's negative, so it's going to be attracting the positive 6.0 Coulomb charge. So it's going to be pulling that charge towards it. So the vector that represents the force here is pointed straight at the negative 2.0 Coulomb charge. According to the original diagram, that means it will make an angle of 45 degrees relative to the horizontal. Alright, so that's a diagram of the two forces that are acting on the 6.0 Coulomb charge. All we have to do is add them together to get the total force. The problem is, they're not in the same dimension, so we will have to add them as two-dimensional vectors. So let's call one of the vectors A and the other one B, and let's split them into their horizontal and vertical components. The x component of vector A is going to be the magnitude, 1.9 times 10 to the 12 newtons, times the cosine of the angle, 90 degrees. That's 0. The y component of vector A is the magnitude, 1.9 times 10 to the 12 newtons, times the sine of 90 degrees, which is 1.9 times 10 to the 12 newtons. The x component of vector B is the magnitude, 4.7 times 10 to the 11th newtons, times the cosine of the angle. Well, what's the angle? It's not 45 degrees because that angle is not defined properly. Remember, it needs to be defined counterclockwise from the positive x-axis. So the properly defined angle is not 45 degrees, but 315 degrees. So it's 4.7 times 10 to the 11 newtons times a cosine of 315 degrees, and that works out to 3.3 times 10 to the 11 newtons. The y component is once again the magnitude, 4.7 times 10 to the 11th newtons, times the sine of 315 degrees, which works out to negative 3.3 times 10 to the 11 newtons. Okay, so those are the x and y components. Let's summarize them at the top of the page there. And now all we have to do is add them together. We add the x components together in order to get the x component of the final vector. So C, the final vector, the x component, is ax plus bx, or 0 plus 3.3 times 10 to the 11 newtons. That works out to 3.3 times 10 to the 11 newtons. Cy is simply ay plus by, or 1.9 times 10 to the 12 newtons, plus negative 3.3 times 10 to the 11 newtons. That works out to 1.6 times 10 to the 12 newtons. So now we know the x and y components of the total force. Let's summarize those as well. To get the magnitude of the total force, we simply take the square root of the sum of the squares of the x and y components. and that works out to 1.6 times 10 to the 12 newtons. To get the angle, we take the inverse tangent of the y component over the x component, and that works out to 78 degrees. Now it turns out that this angle is properly defined because both the x and y components of the final vector are positive, so we're in quadrant 1 of the Cartesian coordinate plane. So the total force on this 6.0 Coulomb charge is 1.6 times 10 to the 12 newtons directed at an angle of 78 degrees.